Okay, so I'm going to try to give you an overview of proof complexity, and I'll talk about like standard propositional proof systems and also the algebraic and semi-algebraic ones that people have been studying for the last roughly 20 years. And if you have any questions, I know I made slides, but it's meant to be relatively informal, so feel free to interrupt or ask questions. So I'm going to cover probably too many proof systems for your liking, but hopefully I'll describe them in a way that you'll see that they're all related to one another. And then I'm going to interleave things. So I'll talk about propositional proof systems, and then algebraic ones, and then semi-algebraic ones. And I'll tell you about some lower bound methods, and I also want to tell you about some applications of the lower bounds to negative results in algorithmic design. And I'll end with open problems. And this is like the first part of a proof complexity tutorial. The second half Pavel will give, and we didn't coordinate exactly, so he'll go into more depth on some of this stuff, and he'll cover things that I'm not talking about at all. Okay, so I'm going to start with propositional proof systems. This is an old subject starting in the early 70s. A paper by Cook and Reckel started it all. And they basically defined a proof system to just be more or less a canonical co-NP complete problem. So a proof system is just a function that takes strings, which you view as alleged proofs or encodings of proofs, to unsatisfiable formulas. Okay, and so that's what this is. Intuitively, it's a function that maps encodings of proofs to encodings of unsatisfiable formulas. It doesn't probably look like what you think of as a proof system. So what you should think of is the proof is the input, and the proof system verifies that it's a proof and outputs what it's a proof of. Okay? And most proof systems that you can think of, any standard textbook style proof system that you've seen, it's usually rule-based. So you're given a bunch of axioms and a bunch of rule schemas, and you can see that they're all really easy to verify that they're proofs, because you just look at the lines and you check that they follow from one of the finite number of rules or axioms. Okay, so pretty much all the standard proof systems that you've seen, or that you may have not seen, but all the standard ones out there are this function is easy to compute. Okay. And the proof system is said to be polynomially bounded if for every unsatisfiable formula f, there is some proof string, okay, where the proof system S maps the proof string to the unsatisfiable formula f, and the length of the string should be polynomial in the length of f. Okay, so it's considered to be polynomially bounded, meaning that every unsatisfiable formula has a short proof, and that short proof can be verified efficiently. Okay, so the proof system S should be polynomially bounded, so it should verify the proof in polynomial time, and the proof system is said to be polynomially bounded, or in other words, has short proofs for everything if every unsatisfiable formula has a short proof. Okay, so this is this is probably not true for any proof system. So the question of whether there's a polynomially bounded proof system is equivalent to the question of whether NP equals co-NP. Okay, because unsat is a co-NP complete problem, and if you had a proof system like this for every unsatisfiable formula, it's an NP algorithm, right, that determines whether a formula is unsatisfiable. Okay, so the existence of such a proof system is just a fancy way of expressing does NP equal co-NP. Does that make sense? Okay.
You can have your slides available?
Yeah, I'm going to mail them, and you'll have them. Yeah. Okay, so that's what I already told you. This is like a theorem from, I forget exactly when, maybe 79. And Cook and Reckel, this was the starting point for their paper. What they then did is study all the classical proof systems in the logic literature, like Frege systems, resolution, sequent calculus, Gensen systems. There's a whole bunch of different ways, natural deduction. There's a whole bunch of different ways to formalize a propositional proof, and they more or less categorized them and looked at which ones are equivalent to which other ones under the unnatural notion of equivalence. Okay, and what they figured out is that pretty much all of the standard ones, except for resolution, almost all the standard ones were polynomially equivalent, and we refer to them all now as Frege systems. Okay, so I'm going to cover those standard proof systems, those are the propositional ones. And we'll also talk about some algebraic proof systems and some semi-algebraic ones. And you can view them all in the same, you can compare them all by kind of viewing them all as proof systems for unsatisfiable formulas, even though these two are more general in that they apply, in this case, to systems of polynomial equations that are unsolvable, and here to systems of polynomial inequalities that have no solution. Okay, but we can sort of view them all. We can just translate an unsatisfiable CNF into a system of low-degree polynomial equations or to a system of low-degree linear inequalities, and so we can compare them all to one another. Okay. So this is the big zoo mess, and I'll try to go through this. And I didn't even put a lot of them on there. So if you want to know where anyone sits, you can ask me, but I was trying hard to not bombard you, even though I know it looks like I am. So here's some of the standard propositional ones on the left. Basically, you can think of all of these as the same proof system. It's some sort of rule-based system where you have a finite number of axioms and rules. And what differs here is you basically impose a restriction on what the allowable formula is, what the complexity is of the allowable formulas in the proof. Okay, so Frege is sort of the standard one where you're allowed to write down any polynomial, any formula. The lines are in any formula, and so polynomial-sized Frege proofs, the lines have to all be polynomial-sized formulas. Okay, and this is like the most standard one. Extended Frege is where you generalize it so the lines can be polynomial-sized circuits instead of formulas. And here, these are weaker proof systems. Here the lines are bounded depth circuits. Here the lines are just clauses. And this is, anyways, we won't get to these ones really low down. Right. So what you do is you start with, it depends if you want to prove a tautology or refute an unsatisfiable formula. But if you, in either case, if you want to refute an unsatisfiable formula, you start with all the clauses as the axioms, and then you have rules that allow you to derive new lines from previous lines. And you're looking at the syntactic structure of the lines. So if the lines are arbitrary formulas, then it's a Frege system. And the rules is just, you have to just specify some finite set of sound and complete rules. And there's a gazillion ways to do that. But they're all more or less the same. Okay. Questions? So the arrows are sort of, I'll get to it in the next slide, but it's what system can polynomially simulate another system. So if it's below, it means it's weaker, meaning that if you have a proof in this system of any arbitrary unsatisfiable formula of a certain size, then the system above it also has a proof of that thing of roughly the same size. So it could be a polynomial factor larger, but typically it's not larger at all. Okay. Yeah, so the point is that the rules are all very local, and they're all just based on, so for example, one rule, a standard rule is the rule of modus ponens. So from A and not A or B, or you can derive B, okay? Or you could write it as, another way to write it is, not A or B. This is slightly different, but. So this is called law of excluded middle, and it's basically from A you can derive, maybe I'll make it the same so it looks, maybe I'll make it look the same. So this is like from A you can derive D, and from negation of A you can derive D, so therefore you can derive D. Okay, so the point is the rule, the only logical connectives that are relevant to the rule, so that enable you to sort of verify the soundness of the rule, are the connectives that I've written. So these can be arbitrary formulas of arbitrary complexity, but they don't really enter into the soundness of the rule. They're very simple rules. Right, but typically the rules, you have to write down the rule. It has to be finite. A finite size, not depending on n. So, Not for the propositional proof systems. We will, when we talk about the more algebraic ones, there we get into more complicated, a little bit more. But in general, because the rules are finite, they can only really depend on a finite number of connectives, independent of n, where n would be the length of the formula that you're trying to prove, which is also proportional to like the number of variables typically in the formula. Yeah, please ask these questions because they're really important to get the intuition behind what's going on. That's right. And that makes sense, right? Because, you know, if it's depending on a finite number of connectives, you could just write down the truth table to verify it, and then any other proof system that's complete should be able to verify that truth table. And in general, that's something to keep in mind. If you can prove something and the proof just depends on a constant number of the upper level of the connectives of the formula, then you can just do it. The most trivial proof, and any proof system should be able to do it. Okay. Mm-hmm.
Is there any place, or I mean, in general, are systems used that do not assume the rule of the excluded middle? So basically, classical logic but divisionistic systems?
Yeah, people do study those. I'm not going to cover those today. And you can also formulate, you can also formulate a system that's not intuitionistic, which is a version of the sequence calculus without the cut rule, and it's a very weak system. But
so, I mean,
you don't need the cut rule for the system to be complete.
So those would be weaker than what we see here.
Yeah, those sit. I mean, they're a little. Yeah, basically they're sort of more at the resolution level, okay. But you have to be a little careful how you compare. Yeah.
So are lower bounds for any of these proof systems equivalent to NP versus co-NP?
No, so that's a really good question. We don't know if there's a strongest proof system. So I drew the standard ones, but you know, you could view any proof system at all, even for a second order logic or whatever, even Zermelo-Fraenkel set theory, you can view them as proof systems for propositional formulas. They are proof systems for lots of things, including propositional formulas, and they have extremely complicated axioms, but nobody knows how to make use of those complicated axioms for propositional formulas. So, you know, there's a possibly infinite hierarchy of proof systems where each one is stronger than the one below it, but we don't even know that. We don't know if there's a strongest one. So proving lower bounds on these proof systems, it really doesn't seem to it doesn't seem like it's going to eventually lead to the agenda of proving NP not equal co-NP. At least we don't know that today. On the other hand, it does seem like I don't know of really any propositional tautology that has a proof that's not formalizable in one of these systems up here at the top. So, yeah. Any other questions? Okay. Okay, so resolution, I'm going to start at the very bottom. Down. I'm not going to talk about truth table proofs. It's just to have a baseline.
So the NP and co-NP has to be a proof of the form that any propositional like proof, you have a lower bound for it, right? So
that's right. That's right. So you have to go back to the function definition.
The function that we have proved for any proof
yeah.
system.
And if we knew, that's right, if we knew that there was one proof system that was the strongest, then we would be able to say, okay, if we could prove lower bounds for that proof system, it'll imply lower bounds for all of them. We don't know that. So.
Are all these known to be non-polynomial?
No. So I was going to get to that. I have a slide that has a line through it, but basically the line is right here. Yeah, he wanted to know where we have, for what proof systems do we have lower bounds, superpolynomial lower bounds. And to cut to the chase, it's right here. So it's a pretty interesting situation. And I'll talk about that more. Yeah. Okay, so resolution is one at the very bottom. I don't want to spend too much time on it. But for most of these proof systems, you can assume that the underlying formulas that you're trying to prove, if they're tautologies, are DNFs, or if you're thinking of the proof system as refuting unsatisfiable formulas, you can view them as unsatisfiable CNFs, okay? And that's just because you can use the usual conversion to take an arbitrary formula and convert it to a CNF or a DNF, okay? And resolution only deals with CNF formulas. Okay, so the input to a resolution proof, or the output, sorry, I should say, is a CNF formula C. So it's a bunch of clauses over some set of underlying variables. And the resolution rule, there's only one rule. That's what's so nice about it. And it lets you take two clauses that were previously derived, or their input clauses, part of the unsatisfiable formula, and you can derive this clause here. So here A is a disjunction of literals, and B is also a disjunction of literals, and you're resolving away the variable x, and you end up with a disjunction of all the other things. Okay, so it's called the resolution rule. And in a resolution proof, you start with your clause. Visualize it as starting with your clauses at the top. So you might have, x or y. I'm going to write down something really stupid. So you might have this as your unsatisfiable formula at the top, and you just apply the rule in some order. That should be a negation. In some order, and the goal is to derive the empty clause. Okay? And the reason people love this proof system is that it's just so simple. There's only one rule, and it's just a matter of applying it over and over again until you eventually get to the empty clause. And it is a sound and complete proof system. Okay? The size of the proof is just the total number of intermediate clauses that you have to use to derive it. Okay? So here's another example of a proof. Sorry, I flipped it upside down in this picture. I think I stole this from somebody. So at the bottom here are the clauses that you start with. Okay? And like I said before, you just pick two of them, and as long as this one has a literal in it and this one has the same literal negated, you can resolve to get the disjunction of the other things. And if you have two copies of the same variable, you think of a clause as a set of literals, so you don't repeat that literal. Okay, so you can resolve these two to get this clause, and so on. That make sense? Okay, this is called a tree proof because the structure of the DAG is a tree. Okay, you ignore how many times you use the leaf clauses. You might have to use the leaf clauses more than once, but all of the internal clauses that you derive, if they're only used once to derive another clause, then it's called a tree proof. And it's also referred to as DPLL. Davis, Putnam, Loveland, Logman, or something like that. Okay? And tree resolution proofs, so all they really are is decision trees. So if you view the proof going down instead of going up, then you can think of the proof as starting at the top and picking a literal. So here I pick A, and on the left I assert not A, and on the right I assert A. And I just keep doing that until I violate a clause. So when I assume that A is false and B is false and C is false, then I can write down this clause at the leaf here because it's been falsified. Okay? So DPLL resolution proofs, all they are is decision trees for verifying the unsatisfiability of a CNF formula. Okay? And you can check that if you resolved on a literal C, that corresponds to querying the literal C. Okay.
So do you mean that the leaves correspond to different clauses? Like in decision trees, any function has a decision tree?
Yeah, this is just an illustration. You're right. So because you might have to use this clause more than once, it can appear in many leaves, possibly.
Any unsatisfiable thing has a...
Yes, any unsatisfiable. All of the proof systems I'm talking about, they're all sound and complete. Yeah. So for any CNF, you could just make the trivial decision tree of height n and size 2 to the n, but that's overkill because some of those paths you will have queried variables that you didn't need to query. So a DPLL procedure, it just truncates whenever it first finds a clause that's violated. Okay, that's the only advantage it has over like truth table. Okay, but that actually turns out to be a huge advantage. And DPLL is one of the most common algorithms for solving SAT, for complete systems that solve SAT. Okay. I mean, I could give a whole lecture on that, but I'm not going to. So I wanted to just point out to you that you can, if you're uncomfortable with Frege systems, this may or may not help you. One way to think of a Frege system is to view it as a decision tree, just like we did before, but instead of querying literals, you're querying formulas. Okay? So, so at the top here, I might pick the formula F that has nothing to do with the underlying C and F. Okay? And I'm going to check what happens when F is false and check what happens when F is true. Now the difference between this and resolution is I'm going to start off asserting that all of the clauses are true. So I start off with the C and F. I'm starting off asserting that each clause is true. And then now when am I allowed to quit? So I'm allowed to quit at a leaf if all of these formulas on the path to here plus the fact that all the clauses are supposed to be true, if I can get a truth table contradiction. So what does that mean? That means, for example, that I get to a place where I've asserted F is true, A or B, and say I've asserted that H is true, and this is not a good example. Yeah, I really wanted to say. Oh yeah, good. Good, thank you. So we're doing which path? Which path? F? The leftmost. So what happened to G? Oh, that one?
You can do F, not H, not F2.
Oh, I guess I'm doing that one. F, not H. Okay, thank you. Yeah, okay, so when F is true, H is false, and F2 is false, then that's called a truth table contradiction. Okay, because this is true, this is false, so that violates the truth table definition of, or and negation. Does that make sense? So it's like a local contradiction, the same way I was trying to explain before. No, A and B are arbitrary formulas. So if A and B were literals, it would be like a resolution contradiction. But here, A and B can be arbitrary formulas. So in this case, A is who knows what it is, and B is who knows. Does this make sense? It's not allowed to. So it's not allowed to. Yeah, it has to basically, it has to basically look like, if the underlying connectives are or and negation, it has to either have on it A and not A for some A. That would be a contradiction to negation truth table. Or it has to be, A or B is true, A is false, B is false, or some other way to contradict A or B. Okay.
Does it have to be syntactic?
Has to be syntactic. And like I said, it can involve the original clauses because that's the only way we're going to get a contradiction. Okay. Unless we...
Even in these Frege systems, the atoms in some sense are these bigger formulas, but the rules are still the mod exponent rules.
So I'm giving you a definition that doesn't have any... I've sort of suppressed... there's only one rule. If you want to think of this as I was trying to give it to you without rules. I was trying to give it to you in a way that maybe would be easier for you than the rule-based one. But if you wanted to convert the system to rules, it has one rule, which is that one up there, that law of excluded middle, and it has a bunch of axioms, and the axioms are these truth table things, that it can't be the case in A and not A, it can't be the case, okay? And I think in some sense that's the most natural. You think of all the axioms as corresponding to like truth table definitions of or and not, if those are your two connectors. And then you just have one rule, which is the rule that lets you say, okay, if something's false under not F and something's false under F, then it's false. Okay? Did I lose you? Are we good? Okay. Okay, so like I said, the getting various proof systems then really just amounts to putting restrictions on what those formulas, all these formulas that you're allowed to query in the tree, you're putting restrictions on what they're allowed to look like, syntactic restrictions. Okay? So tree resolution, you're just allowed to query literals. So you start off knowing that all the clauses are true, and all you're allowed to do is query literals, and you have to get a truth table contradiction. AC0-Frege, you're allowed to query AC0 formulas, and so on. Okay. AC0P-Frege, you're allowed to query bounded depth formulas that have mod P gates. Okay, and there, for this system and this system, since it's an unbounded fan-in or gate and unbounded fan-in mod P gate, I have to modify my my truth table contradictions to deal with unbounded fan-in, but that's not hard to do. Okay. Any questions? So it is different than circuit complexity because, syntactically, if you viewed the proof as a proof of a tautology, every single line in the proof would correspond to a formula that's identically true. So semantically, not a whole lot's going on. So that's a big difference, and one that's kind of really hard to get around. So I'm going to skip the sequent calculus. And like I mentioned before, what polynomial simulation be, the way you compare two proof systems is this notion of simulating. And I said this before, a system A simulates B, polynomially simulates B. If anytime you have an A proof of a certain size, anytime you have a B proof of a certain size, then you also have an A proof of size that's not much larger. Okay? Okay, and, oops. Yeah, and those are the proof systems that I've talked about so far. Okay?
I have a question. In the definition of AC0-Frege, so do we only allow tree-like proofs or do we allow a general DAG?
Right. So the reason we can restrict attention to tree-like is that it turns out that above resolution, tree-like is equivalent to DAG-like. It's a little trick. I could show it to you later if you want, but that's a good question. For resolution, there is a difference. DAG proofs are stronger. But we know how to deal with resolution, so I'm not going to focus too much on that. Okay.
Yeah, I'm not sure I got the definition of AC0-Frege. So you get a bunch of, the thing you're trying to answer what is a CNF.
Yeah, just think of you always start off with you always start off with the unsatisfied.
The thing that you're allowed to query in the tree that we see is arbitrary.
Arbitrary. So this is over variables x1 through xn, and you're allowed to. That's right. You're allowed to query if you want a polynomial size AC0-Frege proof. You're allowed to query arbitrary poly-size AC0 circuits.
There will be some contradiction to those formulas
Yep.
and one of those.
That's right. Exactly. And the size of the proof is just the sum of all the connectives in the proof. So it's like the sum of the sizes of all the. Exactly. Yeah.
So, extended Freges, what could be more powerful than
I know. Good question. Well, like I said, you can view Zermelo-Fraenkel set theory you can view piano arithmetic. They're all proof systems, and they all have more powerful axioms. They have complicated induction, complicated axioms, but we don't know that they're really of any value for propositional statements. That's another example, yeah. So it's a great question. I don't know the answer. Yes, yes. Yeah. Yeah, I think the simulations are kind of intuitively clear. The way I set it up. It might not have, the way in 79 there wasn't this view, so it was a little more effort to, tedious to show that from each set of rules. But I think intuitively it's clear that if the things that you can cut on, this is called a cut, what you're querying. If the things you can cut on is from a strictly stronger class, then you're strictly stronger, or no weaker at least. Yeah.
So when you say query, what do you mean? Because that's an AC0 circuit, right?
Yeah, so I'm thinking of when I view the proof as this tree, the way I showed you. The only rule is this one up here. Okay, and I'm querying A. If I apply that rule, that's like querying A.
So when you say querying an AC0 circuit, what do you mean when you have something like that?
So these are AC0 circuits. They're just,
The input is also an AC0 circuit.
Yeah, you get for free when you start. At the very top of the proof, you get for free C1 is 1, C2 is 1, Cm is 1, because you're asserting that the formula is true even though it's false.
Okay. The C1 that you get is an AC0 circuit.
Yeah, each of the...
Your input is also an AC0 circuit.
Yeah, but you're thinking of building a tree where at the very top you're getting for free to assert that all of these, height 1 AC0 circuits are true. Okay? Right? This is just a clause.
Yeah.
They're just clauses. Okay?
But then I mean I can make just a big clause of all.
You can do that. You can do it, but how are you going to verify that in a truth table fashion? It's a very good example. You can definitely query, you can query this. You can ask, is this true? And, well, I'm going to say you better say it's true, because if you say it's false, it's going to be pretty quick that you're going to derive a truth table contradiction to this. Okay, so if you query this, on the one hand, you're going to say it's true. On the other hand, you're going to say it's false. Okay, on this branch, it's going to be pretty quick to get a contradiction. Okay, because you're saying the whole thing's false, but here you're saying the whole thing's true. So you can just query them one at a time. And
Querying, you mean like using one of the axioms?
no, I mean literally asking. I mean, so what I mean is ask about C2 and Cm. Is that 0 or is that 1? Okay. So keep asking about subformulas of this until you force a lie. Okay, so this side is going to be easy, but the point is here you've really made no progress at all, and so you're right back where you started to some extent. Okay, so you really have to do something non-trivial. Look inside C1. Look inside this and try to understand why it's false to make any real progress. Okay. All right, so let me tell you about some lower bound methods that we have for propositional proof systems. There's basically three. Something called width-based method, and that works for resolution. It also works for some algebraic and semi-algebraic proof systems that I'll hopefully get to. Second method is called the interpolation method, and that works for resolution and the proof system called cutting planes. And then we do have a lower bound for AC0-Frege, and this is quite different than the other two, and it uses the switching lemma in a non-trivial way plus a non-trivial proof complexity argument. Okay, I'm not going to tell you anything about this one. It's a little too complicated, but I will tell you a bit about the other two. Okay, we okay for time? You don't need a break? Okay, so let's start with a width-based method. This idea was around ever since the first resolution proofs, but it was really made explicit by Eli Ben-Sassoon and Avi Vigderson, who proved that more or less, if you start with K-CNF formulas, if you can prove that any resolution proof of a K-CNF formula has to at some point have a wide clause, in other words, a clause that has lots of literals in it, then that more or less automatically implies size lower bounds for resolution. Okay? So they proved an equivalence between size of resolution proofs for K-CNF formulas and width. Okay? You can do this, like I said, with the general size width trade-off due to Ben-Sassoon and Vigderson. You can also reduce from size to width using a restriction argument. Sometimes one or the other is better. So if you do it directly with a restriction argument, you can often get a better result. But if you're lazy, you can use the general size width trade-off, and that usually is enough to make things work. Okay. So what do you do when you prove a width lower bound? You want to show, and width lower bound is basically proven by you looking at the hypergraph associated with the KCNF that you start with. And as long as that graph is sufficiently expanding, it's very easy to show that a resolution proof has to have big width. Okay? So I'm going to show you how to do that. Okay, so this is a picture of a bipartite graph associated with a KCNF formula. Okay, so you have a node for each clause on the left and a node for each variable on the right, and you just draw an edge. For this clause, you just put an edge if that variable occurs in the clause, either negated or not. Okay, and if it's a KCNF, the out degree here will be K. Okay, and gamma S is the set of neighbor. If you have a subset S of initial clauses, so these are the initial clauses, the clauses of the original unsatisfiable formula. Okay. And so for a subset of these clauses, gamma S is the usual notion of the neighborhood set of S, and delta S is the unique neighbors of S. So it's a set of variables that are in exactly one of the clauses in S. Okay? And the graph is said to be an NE expander if for every subset S of size at most n, the neighborhood set is at least E times size of S. Okay? And it's a boundary expander if for every set of size at most n, the size of the boundary is bigger than or equal to E times size of S. Okay? Boundary means unique neighbors. And it's very easy to show, just with a little counting argument, that if you have a graph that's a pretty good expander, then it's also going to be a small loss in parameters, but it's going to be a good boundary expander. Okay? So this is how you prove a with argument, assuming that you start off with a formula, a KC and a formula F, whose underlying bipartite graph is a good expander and therefore a good boundary expander. Okay? So F is the formula that we're starting with, and mu sub F of C. This is, so C here, think of C as being an arbitrary clause that might be in the proof, might be in the refutation. Okay? And it's just defined to be the minimum set of initial clauses that's needed in order to derive C. Okay? So it's the minimal number of clauses such that those clauses implies C. Okay, and you should think of that as, if I want to derive C from the initial clauses, since I start with something that's unsatisfiable, I can derive anything, and the question is how many of the initial clauses do I need to derive it? Okay, and there might be more than one way to derive it, but I'm looking at the minimal number of clauses that I need to derive it. Okay, and that's sort of the complexity of this clause C. Okay, and this measure is subadditive, so. If you derive a clause C from two previous clauses, C1 and C2, by the resolution rule, you should sort of visualize what's going on here. If these are the original clauses used to derive C1, and these are the original clauses used to derive C2, then certainly all these clauses derive this one. Okay? So it's subadditive. So if the empty clause requires at least n initial clauses in order to derive it, okay, then there has to exist a clause in the proof whose complexity is, say, between n over 4 and n over 2. Okay, so you just start at the top. The initial clauses have complexity 1, and you just find the first clause on the way down whose complexity is n over 4 or greater. Okay, and since the measure is subadditive, the complexity of that clause can't be more than n over 2. So it lies somewhere between n over 4 and n over 2. Okay, and now I've found a subset S of clauses of size between n over 4 and n over 2, and since the graph's an expander graph, okay, this set of clauses has a big boundary, okay, which means there's a lot of variables in this subset of clauses that occur in exactly one place. And what does that mean? Anybody know? That's right. If the clause is sitting there and it's used to derive C and it's sitting there, if a variable is sitting there and it's only sitting there one time, then I couldn't have resolved it away because it either occurs positively or negatively and not both. So that means it's going to survive. It's still going to be sitting there in C. Okay, so that means C has to be wide. Okay?
So this can be used to show for random CNS.
Yeah, exactly. It's basically used to show the lower bounds that we have all. Sometimes the argument is a little more complicated than this because sometimes the expansion is a little more hidden. But it's basically this is what's always going on. So does it make sense?
Sorry, I'm lost.
Oh no, if you're lost, then I need to repeat.
But you started with the contradiction requires.
Yeah, so I start, I don't know if this helps to visualize it, but I have all the initial clauses sitting up here. And I know that, let's take the case where I need them all. That's the easiest case. So I need every single clause to derive a that means if I take one out, it becomes satisfiable. So in that case, the measure for the empty clause is M, all of them. Okay, so that's the easy case. And then I'm just going to find the first, pick an alleged resolution refutation and then find the first clause in the proof that's been derived from, say, n/4 initial ones. Okay? and that clause is going to be derived from somewhere between n/4 and n/2 initial ones. Okay, so if I look at that subset of initial clauses, let's say it's these. Okay, since it's a medium size, it's a set S on the left of the expander of the bipartite graph, and it's expanding. Okay, so it has a lot of variables in it that occur exactly once, and they have to be still sitting inside C. Does that make sense? This tells me that C is wide, and then I'm done. So now I've proven that in any resolution proof, no matter how big it is, doesn't even use anything about the size of the proof. It could be exponential sized. Any resolution proof has to have a clause C in it that's complex, meaning it's wide. Okay, and then to go from that to a size bound is, like I said, you either use this general size width trade-off that's not complicated, or you just apply a restriction argument to take a small, and that's where you need the size thing. So you take a alleged small proof and you hit it with a little restriction to kill off all the wide clauses, and then you're done. Or you apply the more general size width trade-off result.
So is this size width trade-off just like balancing formulas?
No, it's more or less very similar to a restriction argument. You're basically querying variables to kill off the wide clauses.
So it's like yes, for polynomials.
Oh, I don't understand that, but okay. You can translate that. Okay.
Sorry, what's the statement from this side? So when you show a width low bound, does this imply?
Yes. So I didn't state it, but Ben Sassoon-Vigderson showed that if you have any resolution refutation that requires any resolution refutation of size bigger than or equal to S requires. Am I saying it the wrong way? I need a. Well, that's okay. Okay, so Fs is something like 2 to the, no, S requires width, so it's something like square root of n log S. I forget if the square root is under the log or not, but it's roughly that. Okay, so if you have a proof of polynomial size, then you have a proof of width, n to the epsilon. That's right. No, it's not the same one, and the proof could blow up in size. Yeah, and there's a result in the other direction too that's fairly obvious. So, if you have a proof of small width, then you just count the number of clauses of that width, and okay, so that's that argument. Sorry, I already did this, so I'm going to skip it. Any questions? We're good? Do you need a break? Should I move on? Okay, good. It'd be good to be done with the propositional stuff before we take the break. Okay, so the other methods I won't tell you as much about. I won't really show them to you. The second method that's been very productive is called feasible interpolation. And the idea here is that you associate a search. This is used a lot, this idea of a search problem. It's used not just with feasible interpolation, but it's used to get lower bounds for almost a lot of the lower bounds for the semi-algebraic and algebraic proof systems use this. They don't use interpolation, but they use the idea of looking at the search problem associated with the CNF. So I want to tell you what that is. So you have this unsatisfiable CNF, and you can associate a search problem with it. And the search problem in general, don't look at the slide yet, the search problem is given a truth assignment alpha to the unsatisfiable formula, output a clause that's false. So that sounds really stupid, I know. because you just go through the clauses. But we're going to be in a model that's very restricted, so that you're not going to be allowed, you're only going to be able to look locally at the clause. Okay. So I'll talk more about that in a little bit. But that's the search problem associated with an unsatisfiable formula. And there you can make it a decision, not really a decision, but you could make it a 0-1 search problem by splitting up the clauses into two groups and asking, is the contradiction on this side or on this side? Okay. And so that's a search problem, another search problem, a little bit easier search problem associated with the CNF. The interpolation search problem is related to that. It's a version of it. So you're starting off with a special kind of CNF formula that A is a bunch of clauses and B is a bunch of clauses. And they share P, Q, and R are vectors of variables. Okay, and they share the variables P, and they have private variables. A has the private variables Q, and B has the private variables R. And this is a variant of what I told you before. The search problem for A and B is given an assignment alpha to just the shared variables P. Okay? And if the formula is unsatisfiable and you set all the shared variables to a value, you're left with two disjoint formulas. Okay? And since by disjoint, I mean they're variable disjoint. And since the thing's unsatisfiable, this means one of the two by itself has to be unsatisfiable. Okay, in the search problem, the interpolation search problem is to determine which side is unsatisfiable. They could both be unsatisfiable, in which case you can say either one. But obviously, if just one or the other is unsatisfiable, you have to know the difference. Okay. Okay, so that's like the interpolation search problem associated with this kind of weird statement, this interpolant statement, where you have two parts to it, where they have shared variables and private variables and shared variables. And a proof system is said to have feasible interpolation if you can always solve this search problem efficiently in the size of the proof. Okay, so if you're in a proof system S, and any time it has a proof of a statement of that form, if you can extract from the proof a small circuit that solves this problem, okay, then the proof system is kind of weak. It has feasible interpolation. Okay, because so you can think of this instead of an and as I guess you're trying to interpolate. I don't know. I don't have a good answer. I think it's because you're trying to interpolate. Like you can think about having a bunch of these, and you're trying to interpolate between. I don't know if it's related to the calculus notion. Yeah. Right, but why is it used there? It's definitely from Craig interpolation, but.
So you're putting something inside, so you have to negate one of the, so say it's A and B or not A and B.
No, I know, but is it related to interpolation from
No, but like you put something in the middle, you interpolate it.
Yeah, right. That's what I was trying to say, but then I realized that's not really interpolation in the calculus sense. Did that help? No. Okay. Anyways, it doesn't really. We're on the same page, but I don't know if that helps. And you can prove, and this is not very hard to show. Oh, there's a monotone version of this too. So the monotone version is the statement itself has to be monotone. And what that means is that, say, the A part, the variables P, can only occur positively. Okay? And if that's the case, then the search problem is also, in a sense, monotone. So meaning that if you change any of the alphas from zeros to ones, if you already said A before, if A was the answer before, it's going to continue to be A. Okay? So if the statement itself has the monotone form, then you can talk about monotone feasible interpolation, because the search problem is monotone. So you say the proof system has monotone feasible interpolation if any time you start with a monotone interpolant statement. If you have a proof of it in proof system S, then you can extract a monotone small circuit for solving the search problem.
Okay. Why is it difficult to solve this search problem using the circuit? Can you just try one clause after the other?
No, because these are two once you make an assignment to the p variables, you have two totally disjoint, unsatisfiable formulas, and you want to know which one's unsatisfiable. So in a sense, you're trying to solve SAT. Yeah, so you don't have an assignment to all the variables p, q, and r, just to the p stuff.
No, so the difficulty is that your circuit needs to compute this thing on all the alphas.
That's right. The circuit takes as input an alpha. That's right.
And that also sounds like a polynomial that interpolates something that, yeah. I mean, it makes sense. You maybe not yet, but okay,
So let me show you some examples of interpolant statements. So there's the clique, co-clique example, where the p variables describe a graph, okay, and the q variables describe a k clique in a graph. So it's like a list of k vertices. And A says that the variables that q says are in the k clique really are in the graph p. Okay. And B, on the other hand, says that same variables p that describe a graph, but now the R variables are describing a partition of the vertices into k minus 1 pieces. So the B part is trying to say that R, that P contains an independent set of size k minus 1. Okay, and of course that's a contradiction because the graph can't contain both a k clique and a k minus 1 coloring. Yeah. Okay. So, and you're trying to distinguish between the two. You're trying to determine, given a graph P, does it have a k clique or does it have a k minus 1 coloring?
How is the reduction to lower bound code? Is it via some computation complexity game?
You mean to prove that a proof system has interpolation?
No, how interpolation, why does interpolation imply lower bound?
Oh, so I'm going to show you that. Okay, so let's say that you can solve. So this turns out this is a monotone interpolant statement because the more edges you put in the graph P, the more likely it is that the graph is that Q is a k clique in graph P. Okay, and a monotone circuit that solves this, we know by Rasbroff's theorem that there is no small monotone circuit for this problem. Like given a graph, does it have a square root of n clique or a square root of n minus 1 co-clique? Okay.
And it's immediate, this transition between the graph lower bounds and the
You have to prove an interpolation theorem for the proof system. So you start with like a proof system like resolution or cutting planes that have monotone feasible interpolation. You have to prove that. That takes some work. Once you prove that, then this statement itself, you start with this statement and you want to show that the proof system cannot prove this with a small proof. Why? Why not? Because if it could prove this by monotone feasible interpolation, I would have a small monotone, from a small proof, I would have a small monotone circuit that solves this problem. And so it's a reduction to the lower bound that we have.
And that circuit takes as inputs Q and R. What does it take as input?
So the circuit for this problem takes as input P, an assignment to P. So just a graph. Yeah. The reason that the interpolation statement is a little weird, a little tricky to prove that a proof system has it, exactly because you're going from 3 sets of variables to 1 set of variables.
It takes P and output 0, 1, A or B.
Yeah. 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 Good? Okay, so this was used to show this is another way to prove lower bounds for resolution, and you can also use this method to prove lower bounds for cutting planes. Okay? Another example, actually I'm going to skip this example. I'll tell you about the last example just very briefly. So you can also write down another interpolant statement that's really interesting, which is you can express a certain version of P not equal NP using an interpolant type statement. So I'm going to express that satisfiability does not have polynomial size circuits. Okay, and the way you do this is the A part says that so P is going to be a SAT instance. Okay, and A is going to say that Q is a circuit for P. Q is a circuit that solves P. Okay. Now, saying this is going to take exponential length because you have to run through all of the. P is just an arbitrary NP problem. I'm just picking SAT, but it could be clique or whatever. Okay. So the variables here are the inputs to that NP complete problem. Okay, and the variables for Q are variables that encode the circuit. And this formula is saying that the output of this circuit on every input is what it's supposed to be. So it has to go through all 2 to the n assignments. So the statement A has size 2 to the n, where n's n's roughly the number of variables that encode the SAT instance. Okay. And B is saying, on the other hand, that R codes a polynomial size circuit for that problem, the XOR of P and SAT. Okay. Yeah, maybe this is too hard to do in a little bit of time. So I think I messed up a little bit how I described this. So P is an arbitrary circuit, okay? P is an arbitrary function, okay, on 2 to the n variables. I messed up. Erase what I said, I'm starting over. P is a function on n variables, so the truth table of it has size 2 to the n. Okay? Q is a circuit, and this is saying that Q actually computes P. Okay? B is saying that R computes the new function f parodied with SAT. Okay? So SAT's another function. It's another function, and it's just I'm taking the XOR 2 to the n length XOR bitwise. Okay, so so this can't be. It can't be that both of these is true. Okay, and it might be a little bit tricky to see that this is basically. So if you could prove this, you can also prove that SAT is not in P/poly. Okay, maybe this is too much for me to do. Yeah, that's right. That's right. And you can show that this formalization of SAT is not in P/poly. You can show lower bounds for this in certain weak proof systems using interpolation.
So by SAT you mean that SAT is a function that given vector of length n treats it as a formula?
That's right. That's right. I'm viewing SAT as exactly what you said.
We have a break.
Yeah. So this is one more minute. So I just wanted to point this out. I didn't expect you to fully digest this, but I just wanted to, at a high level, point out that there's really interesting interpolant statements, not just for the point of view of getting lower bounds for proof systems, but also for thinking about metamathematics of the P versus NP problem. That's why I wanted to bring that up. And also interpolant statements. This middle one is interesting. Again, there's other reasons to be interested in interpolant statements besides just proving lower bounds. That was my high-level reason for telling you about the other examples. And then I just want to tell you for 1 minute about this third method a third method that we have for proving lower bounds for proof systems, which is the method of proving lower bounds for ACO-Frege proofs. You can use this method. It's a very specialized method. It only works for certain formulas. The other methods are much more general. They're easier. They apply to much weaker proof systems, and you can use them for lots of different formulas. This one is very special to the formula that you start with, and we only really know how to do it for, pigeonhole principle and for another example called the Seiton formulas. And it's Itai's method, although then it was generalized to get exponential bounds a few years later. The pigeonhole principle is one of probably the most famous example of a hard tautology in proof complexity, and it's just a statement that you have, in this case, you have 10 pigeons and 9 holes, and it's the statement that you can't stuff n+1 pigeons into n holes in a one-to-one way. Okay, and the variables of the formula are Pij, representing whether or not pigeon I goes to hole j. Okay. And just a few high-level comments about the proof, that at a very high level, you basically apply a very hand-tailored switching, you apply a very hand-tailored restriction to the entire proof in order to allow you to do a switching lemma argument. So you start with I don't know if you're familiar with Hofstede's switching lemma, but there you take a bounded depth D formula, you apply a restriction to it, which enables you to convert it to a D-1 formula, and you iterate this until finally you end up with a small height decision tree where then you can prove directly a lower bound. So at a very high level, that's what's going on here. You start with a bounded depth proof where every line in the proof is a small depth AC0 circuit. You're going to iteratively apply restrictions to allow you to reduce the depth one at a time. Okay, the thing that makes it much more complicated is getting back to what we discussed many slides ago, which is the fact that in a proof, all the lines are basically always true or always false. So you have to be really careful. You have to apply a restriction that's not going to kill off the clauses that you start with. So if you start with something that's unsatisfiable and you apply a restriction that's going to set one of those clauses to false, you're done. The game is over. You're not going to be able to prove a contradiction to something that's false. Okay, so you have to pick restrictions that are going to be really special, that are going to make it look like that it's still possible that there's a one-to-one mapping from n plus 1 to n. So that you're forced to pick restrictions that map some of the pigeons in a one-to-one onto weight to some of the holes. Okay, that's one complication. You have to pick a very special switching limit. The other complication, which is even worse, is that the switching thing only happens in a local way. So you're not able to preserve truth functional equivalence when you do the switch. So you end up with lines that don't look anything like what they really started with. They look totally different. But instead, what you do is the invariant that you maintain is that it preserves a sort of local soundness. Okay, and sort of these are the two things, especially this one, that makes the proof complicated. Okay, so that's it for what I wanted to say about propositional proof complexity. And here's the line so that we have. So let's take a break.